Oh, hello. We're on TV. We were just, this is ECE 637, Digital Image Processing 1. Today is Wednesday, February 3rd. Yes. And we were, okay, how many, there's theoretically a reading day that we could take off. I'm not even sure what day it is, but it's a Wednesday. 2 weeks from now. How many people feel, I don't want to put anybody on the spot, okay? Uh, how many people would prefer to take the day off, the lecture off? You would. Oh, so some would. I mean, it's not, okay. Well, maybe, let me think about it a little bit, and you can discuss it among yourselves, and I'll make a final decision, okay? Basically, if there's a significant minority of the group that, it doesn't have to be a majority, but if there's like, a significant number of people who feel that this would be helpful, I'll default to that, okay? But it's, it's kind of up to you a little bit. But I kind of, the semester is really compressed. There's so many, I mean, it's kind of coming at us like a fire hose a little bit this semester. There's no spring break or anything, so maybe it's not such a bad idea on reconsideration. Okay? Good. So we're talking about tomography. So last time I kind of talked a lot about the applications of tomography. Okay? And then, so the key idea is that, what? The key idea in tomography is that that you have like a, you have this is X and Y, and you have some object. So I have a drawing over here. I don't know. I'll make it a simpler drawing because it's easier that way. A blob that's off axis, okay? And then what happens is that you have integral views. And one thing that's not maybe illustrated so well here is that this isn't just binary. So it's not just like blob on, blob off. It's also continuously varying gray levels. And then what happens is that you take a projection at some angle. So this is theta. There's different coordinate system conventions you can use for this problem. So, and like if you use software, they may follow different conventions. So you have to check. It might be like a clockwise rotation. It might be a counterclockwise rotation. It could be that the zero projection corresponds to vertical integration, or it could be that it corresponds to horizontal integration. So I'm doing a special case here, but it doesn't. It could vary. Okay, and then you have this this point here is perpendicular, like that. Okay, and then that's zero. So the zero axis of this projection goes through the origin of the coordinate system, okay? And then what happens is you have projections. So obviously what happens here is that the projection of this blob is large over where it's thick, and it's not so large where it's not so thick. So you're going to get something like that. Well, it won't be. It'd be like that. This would be the projection. So that's P, and this axis here is R. It's the letter I use. So this is a function of R, but it's a different function of R for each angle. So it's subscripted by theta. And then this thing here is the thing you're trying to reconstruct, and it's f of xy. So what happens is that this measurement you get, which is the projection, is a linear transformation of the thing that you actually wanted to know. So it's linear in the sense that it's an integral. So let's see. I'm sort of jumping ahead a little bit, which I think it's good to go back and forth a little. So this is jumping ahead. But this is the integral relationship. And And I think it should be clear this is an integral, right? Because you're integrating along here. So since it's an integral, that integrals are linear. So it has to be a linear transformation. If you double this thing, that thing will double, right? Or if you have two objects in your view, they will add in the projections. So it's a linear transformation. So if you discretize it, so if you take the image f of x, y, and we'll talk about this in a lot more detail later, but if you take the image f of x, y, and you sample it with a discrete space sampling. We're going to do that later, but if you sample it, you would get, you could represent it by vector, so we'll call that x, right? So this is, I know the notation is a little confusing, but because here I'm using lowercase x I'm using x as an independent variable in the continuous space, but x is the conventional letter you would use for something like this. So you get, that's x, so that's the image. And then you have y. Y is, these are the projections. And now, of course, the entire idea is that you have projections at different angles, not just at one angle. And the relationship between those is a linear transformation. So if you have a linear transformation, if you have a vector, you vectorize these images. And what's the most general representation of a linear transformation in for a vector, basically? Vector is a general representation of any discretized object. Yep, I heard it, I think. Yeah. A matrix, right? That's why matrices are important in linear algebra, because linear algebra, if you have vectors, if you have finite dimensional vectors, a matrix is the most general linear transformation. Any linear transformation can be represented by a matrix, okay? So basically, in tomography, this is tomography. Okay, your goal in continuous space, you look at it this way, but in discrete space, you're really trying to solve a problem which is y equals ax, which is something that should look familiar to you from linear algebra, right? So what's the answer to the question, how do you solve the problem y equals ax? Everybody knows, right? You say that x equals a inverse y, right? Except for you can't really do that for a few reasons. First of all, a may not be square. If it's not square, it's not even invertible. It may be that the number of measurements is not equal to the number of unknowns. So that's one possibility. Or it may be the number of measurements is more than the number of unknowns. So if A is tall and thin, that means you have too many measurements. So you have an overdetermined system. So you know from linear algebra that in that case there may be no solution, right? Or it might be that it's possible there is a solution, but it's sort of improbable because you have general measurements. Chances are there won't be a solution because some of the equations won't agree with each other, okay, because of small perturbations in noise and so forth. Or it may be that you have not enough equations, in which case you have no solution, or there's an infinite number of solutions is the problem, actually. So, but even if you can invert A, X here is an image. Let's say it has 1 million pixels in it, and its measurement has 1 million measurements. So that matrix is 1 million by 1 million. So you can't really invert. You can't even really store the 1 million by 1 million matrix effectively, and you certainly can't invert it. So this is not practical. Which is why we're talking about this, really. If you could do this and it was practical, then it wouldn't be a big deal, right? But so we need methods that are analytical, that can give us the inverse, that can solve this problem, but without directly inverting the matrix, because that's just not a very practical strategy, okay? But the other thing, the main point I wanted to make at this point is that the projections need to be linear integrals of the unknown object, okay? So here, mathematically, each point of p theta r is an integral of the function fxy through lines, projections. Now, the question is, so that's fine mathematically, but experimentally, where are these measurements going to come from, okay? How are we going to actually measure these line integrals? Well, it turns out that there's lots of different physical phenomena that can result in this kind of measurement for different cases. So what ends up happening is that people know that you can solve this inverse problem, so they kind of search around for experimental measurements they can make which give them the desired measurements, right? So if you're a scientist and you're trying to measure something, or you're a medical researcher and you're trying to develop a new imaging modality, you look for ways in which you can measure integrals through something, because you know you can invert it, right? And but there's different techniques for doing that based upon the different methodologies, and that's why you have different kinds of 3D medical scanners, like a CT scanner and a PET scanner. They both are they both use tomographic reconstruction, but they make the measurements in very different ways, okay? So I'm going to describe a particular way that's pretty common, that's based on what's called, that's generally referred to as transmission tomography, okay? Because there's a whole variety of different methodologies based on transmission tomography, and they tend to always be the same. Here I'm saying you have an X-ray source and you have a detector, but it could be other things. It could be like you could have some other kind of they could be electrons in an electron microscope. In an electron microscope, you shoot electrons in a transmission electron. There's actually two kinds of electron microscopes, roughly speaking. There's transmission electron microscopes, and there's scanning electron microscopes. In a scanning electron microscope, you sort of bounce electrons off the surface of a material. It's like a microscope you would have had in junior high. Like, I don't know, if you had a microscope from as a kid, you just look at the top of the sample. Okay, you're looking at the surface. But in a transmission electron microscope, you send electrons through the sample and you detect them on the other side. Transmission electron microscopes are very expensive. They're like, we have like one here. We have actually more than one at Purdue, but they're like a couple $1 million. But scanning electron microscopes are relatively cheap. They're like, there's some very high-end ones, but the basic ones would be like, could be like $20,000, $30,000, which by that standards is inexpensive. I know it sounds like a lot because you could buy a car with it, but it's relatively cheap for those kinds of applications. So in transmission, so you could have transmission electron microscopy. You could have transmission CT, which is what CT scanner is, a medical CT scanner. Or another example is you can do neutron imaging. So instead of these being X-ray particles, they could be neutrons that you fire through a sample, okay? But the sort of underlying mathematics of the problems is the same in any of those transmission cases. But what happens is that you have a sample and, so you have a sample like this, and say it's a homogeneous sample of some material, and you take a particle and you fire it into the thing, right? And it's a little bit of a I don't know. The imagery here is a little bit strong, okay? But I'm going to use it because it's just so vivid for me, okay? If you think of the particle as being like a soldier, okay, going through, like, a little plastic soldier you have fun with, not a real soldier, okay? And it would, at each point it's going through here, it's trying to go through the material, right? At any point, it can the material to this little photon looks like a bunch of particles, atoms, okay? And each atom has electrons flying around it, okay? So if it's lucky, it kind of goes through and it misses all the particles. Okay. But if it's unlucky, it hits an electron or it hits a nucleus. Okay. And if that happens, it scatters, right? It bounces off that thing. It's the way to think about it, maybe. It's not exactly physically accurate, but it's close enough, okay? So in that event, what will happen is if it hits, there's two kinds of scattering event that occur, elastic and inelastic. So if it's an inelastic scattering event, it loses M energy, okay? It's like if you threw a tennis ball against the wall. When it bounces off the wall, it has less energy than it did. I mean, if it's like perfectly elastic bounce, it comes off with exactly the same amount of energy. But that doesn't usually happen. It loses some energy, okay? When it loses energy, the wavelength of the photon goes up, or the energy goes down, and the detector is energy resolving, okay? Hopefully. So you don't detect it. So for all intents and purposes, when it scatters, it's lost. Some of the energy may be converted into mechanical energy and it heats the sample, okay? So if you put X-rays through the sample, it'll get hot, like putting it in a microwave oven. So the probability of the scattering event occurring at any point is pretty much the same, okay? It's a memoryless thing. The fact that it went so far into the sample makes no difference, you know? At any point, it has an equal probability of scattering through some unit piece of material, and that probability only depends on the thickness that it's traveled through and the density, the optical density of the material, which is related to the physical density. The physical density would be the mass per unit per cc, the grams per cc. By the way, what's the density of water at standard pressure and temperature in units of grams per cc? Does anybody know? It's 1. So it's an easy number to remember. If you dig deep into your chemistry, it's 1 gram per cc, which is 1,000 milligrams per cc, okay? So it's not exactly the same kind of density, but it's related, because if you have more the density of a material is related to how many protons and neutrons it has per unit volume, and because the electrons don't weigh much, okay? So if you have a lot of those particles, it's going to scatter more likely. But in any case, there's tables you can look up online. Actually, NIST has them. NIST is the National Institute of Standards, and it tells you what the scattering cross section is for different elements at standard pressure and temperature, like I don't know, aluminum or hydrogen or whatever. Okay, so the point is this. But if you look at the equation, it goes like this. The probability of scattering, so d lambda x, so lambda x is the number of photons that make it to a certain position, x, okay? I'm using x a lot here, okay? So d lambda x dx, so the number of photons is going to decrease as you go deeper in the sample, because you can only lose them, you can't gain them, okay? So that's going to be equal to, it has to be a negative number, and it's going to be proportional to the density of the material. So the density of the material we'll call mu of x, okay? And then times, Now here's the thing. If I have twice as many photons, it's twice as likely that the photons will scatter, right? Because the photons, this is sort of coming back to the plastic soldier analysis, that like all the plastic soldiers, they don't talk to each other. They're completely independent. So if you have twice as many plastic soldiers, there's twice as high a probability that the plastic soldiers will be scattered, okay? So this is also got to be proportional to lambda x, okay? So this is a differential equation. And it turns out you can integrate this differential equation. And by integrating the first equation, you can solve it. And it's easy enough to show that the solution is lambda x is equal to lambda 0. So lambda 0 is the number of photons you have, lambda 0, when you start. And that is times e to the minus and this is the integral from 0 to x of mu t dt. T is just a dummy variable. It's not time. Maybe I should use some other variable like tau. It has nothing to do with time. Okay. So the beauty of this equation, and this is called Beer's law. I'm pretty sure it's spelled like this. And it's called Beer's law, more or less. Beer's law is a little bit, it's usually associated with something just a little simpler than this, which is that when the density is constant. But this is sort of a minor generalization of Beer's law. So the important thing here is that your measurement, is actually lambda x. This is the number of photons you detect. And this is the number of photons you put in. So you can say, well, how do you measure lambda 0? Well, you can get that through a calibration procedure. And then, okay, this is what you really needed to know. So if I take the log, I get that the integral from 0 to x, or to t, 0 to x, right, of mu of t dt is equal to the negative log of lambda x over lambda 0. Now, lambda x over lambda 0 has always got to be less than 1, because as the photons go through the sample, they're attenuated, right? Unless somehow, I guess you could have some kind of exotic lasing material that pumped more photons in. But if it's a passive piece of material, it only absorbs photons. It doesn't create them. So lambda x will be less than lambda 0. And then if you take its log, that will be a negative number, right? Because any number less than 1 has a negative log. So if I take the negative of that, that's always a positive number. So this thing will always be positive. So that thing will always be greater than or equal to 0. It'll be non-negative, okay? And it'll be 0 when there's no sample here at all, okay? So this equation is really important because it tells us how we actually get the linear projections we need to solve the problem. Because what we really need is this p theta r. We haven't talked about how we're going to invert it yet, but let's assume that we just believe that we are. Then how are we going to get this? Well, this is how we physically get it in a real problem, okay? And so what happens is that this is the thing. This is really important. I think the students often don't quite really understand this. So YT is the actual measurement, photon measurement at the detector. So you have some sample. Okay, that's your sample. You have some X-ray source. I'll draw this as the X-ray source, right? And then you have a detector. Okay. What you do is you first measure. You measure. I call it like lambda 0. This is called the blank scan sometimes. You take sample out. So what you do is you just remove the sample. You take it out, okay? And you make a scan without the sample there. And it gives you some baseline measurement of the intensity of the X-rays when the sample's removed. Is that clear? Does that make sense? And then you measure lambda 1. This is put sample back in. Now, of course, this measurement could just be made once because it's the same no matter what you're scanning. You could be scanning, like, I don't know, this pen or this thing here or somebody's finger. It's all the same. The measurement without the sample is always the same. So this is really a calibration scan you do every morning, okay? So if you have a medical scanner, every morning the medical technician comes in and runs a calibration scan to make sure that the scanner is recalibrated for that day. And then they reuse that measurement because presumably it doesn't change too much. But then you put the sample in and you measure it. And then what you do is you take, okay, you take lambda 1 over lambda 0. Lambda 0 is the measurement, is the calibration. The ratio has got to be less than 1, so you take the negative log, and that's equal to y. That's equal to your, this is the actual attenuation that you use to do the reconstruction. Is there any questions about that? It's sort of like simple, and it's sort of like not simple. It's sort of fun, yeah. Okay, so that's this. Now, there are other ways you could do it. In PET, positron emission tomography, they do something that's physically very different, but they get the same kind of measurement, okay? In PET, what happens is that this is primarily, it's called positron emission tomography. This is primarily a medical imaging modality. I guess it could be used for some other things. CT, transmission tomography, is used in a lot of industrial applications. But here what they do is they have a thing called FDG, or fluorodeoxyglucose. So basically what it is, I'm not a chemist, but glucose has an isomer. So you can replace, basically, you can take glucose and you can replace one of the atoms in there, in the molecule, with fluorine. And then you can use an isotope of fluorine, which is F18. And you say, well, where do you get F18? Well, you have to have a cyclotron. So with the cyclotron, you can make nuclear isotopes that are unstable. They're naturally occurring, but at a very low rate, because the decay rate of the half-life of F18 is about 20 minutes or something. Wait, is that right? Yeah, I want to say it's like a half an hour. Maybe I'm off on that. No, it's longer than that. I'm sorry, I'm getting confused with something else. Anyway, it has a reasonably long half-life, but not too long. You don't want something with a super long half-life, because that would be like plutonium. And everybody knows plutonium is not good to have around, okay? Because it has a very long half-life, so that it doesn't go away. But F18 is an isotope which is radioactive, but its half-life is relatively short. So even in high concentrations, after like a day or two, it's gone, okay? Even after a few hours. I have to look this up. I feel like maybe somebody can look it up real quickly, what the half-life of F18 is. So they make this in a laboratory, okay? And then there's sometimes people will have cyclotrons locally so that they can make the F18, and then they have to do the radiochemistry to turn it into the FDG, which is the actual chemical that is essentially glucose. And then what happens is that they have the patient drink it's like a sugar water a drink, and then your body metabolizes the glucose. So the F18 goes to whatever it is that's metabolizing the F18. And now it's primarily used for oncology applications. So if you have cancer, then what will happen is the cancer, actually, one of the basic problems with cancer is it's like a mutation of the cells which cause them to replicate too fast. So they burn too much energy inefficiently. So the tumors will light up because they'll absorb a lot of F18 as they metabolize the glucose. Now, after they metabolize the glucose breaks down, but you don't change the atomic structure of the underlying elements. So it's still F18 until it decays. And when it decays, what will happen is it emits a positron. When it's nuclear, unstable nuclear isotope decays, it emits a positron. The positron goes out. It's the antiparticle of an electron. And it relatively quickly finds an electron. When the electron and the positron come together, they annihilate, right? Because they're antiparticles. And of course, through conservation of mass and energy with E equals mc squared, what happens is that they emit 2 photons, okay? It has to be 2 photons. Why? Because it has to be conservation of momentum. But there's still a little bit of momentum in the positron. So what ends up happening is the 2 photons that get emitted, like approximately get emitted in opposite directions, but not exactly. So it's 179 degrees, they say. It's not exactly 179 degrees, but it's approximate. So So what happens is you get two photons. Now the energy of the photons is such that they're actually gamma rays. Okay, so they're high energy. They're, I guess, above X-rays. I don't know. I have to check that. But they're high energy photons. They go in opposite directions, and that what happens is that you get a ring of detectors. So they put a ring of detectors around the patient. There might be like 512 or 1024. I don't know what the current state of the art is. And this is really cool. They have this high-speed electronic circuitry that detects when the photon was detected within nanosecond accuracy. And then they put it what's called list mode, and they have this process around here that takes all this data. It's like does a matchmaking. So it finds photons that arrived at the same time. If the two photons arrived at two different detectors at the same time, it means that you assume that they must have come back from the same underlying event. So they actually, when I say same time, I would say within 10 nanoseconds. That's called a coincident window. So then what happens is they basically do a histogram of all the coincident photons that came together, and they essentially create what is a virtual detector associated with every distinct pair of detectors on the PET ring. And then when they count that, they get a linear integral of the concentration of F18. So it's another way that's physically distinct for finding tomographic measurements. The underlying idea is to basically get this measurement of this function P theta R, okay, which is the projection. But physically, it's a totally different mechanism. And PET scanners, it's a totally different mechanism to get like an analogous physical quantity, a mathematical quantity. And this is an example of a PET scanner. So this is the actual PET image. And what happens here is that you see that nodule you get. That's probably, I'm not a radiologist, but my guess is that's like a lymph node that has has cancer, and it's a tumor, and it's metabolizing a lot of FDG, so it lights up. Okay, but then you get that. You know what that is? Even if you're not a doctor with a background in anatomy, you might be able to guess that one. You can look at it. Yeah, okay, you can't see it in the slice here. It's your bladder. It's their bladder, okay? So why is the bladder lighting up?
That's where it all goes when you don't use it?
Exactly. Well, it's all where it goes when you do use it. So when you metabolize the FDG, which is sugar, the F18 doesn't change because it's an atomic structure, right? When you take hydrogen and water and if you take hydrogen and oxygen and combine them in combustion to form water, the hydrogen and oxygen atoms are unchanged, right? It's just that they've combined to form a different chemical structure. So the chemistry may have changed. It's no longer glucose. It's been metabolized, but it's still got F18 in it, and it went into the bladder, okay? So in the form of urine, right? That was metabolized. So then if you're taking a PET scan, they have you kind of stay by yourself for a couple of hours, so you don't irradiate other people. But now what happens is here, that's actually a CT scan here. Okay, so all modern PET scanners actually, they look like this. And what they do is they take a CT scanner and they add the PET ring to it. Because the CT scanner is relatively inexpensive compared to the PET anyway. And then when the physicians look at it, it's actually a multimodal image. So because otherwise, if you just see the PET scan, it's hard to orient yourself in the anatomy. So they fuse the PET and the CT image, and they make a color image, and then you can see the radiologist, who's the physician trained to read these images, then can pick out where the tumor is, and then they use that diagnostically to design a treatment plan, which would be either like oncology or radiotherapy or something like that. Okay, so that kind of gives you a sense of how that works. Now, okay, so now I'm going to explain mathematically how this inversion occurs. So first of all, we have a coordinate rotation, okay? So coordinate rotation, we talked about this before. So if we have two coordinates, we have r and z and x and y. So x and y are the native coordinates of the object we're trying to reconstruct. And r is the displacement, right? And z is the direction perpendicular to the displacement in the rotated coordinate system for a particular projection angle theta. Okay? And okay. So now you want to integrate across z. So what you do is the projection mathematically, you take f is a function of two variables, x and y. So you take r and z, you multiply by theta, and you integrate over z, because that's how you're going to do the projection, by integrating along this dimension. Does that make sense? If you expand it out, this with the particular form of this matrix transform that we've discussed previously, then you write it out in a long form. It looks like this, okay? And the cosine theta and the sine theta are doing the rotation of the coordinates. Does that make sense? Do people believe that? Okay, now, so this thing here, this projection is known as the radon transform that you're trying to invert. So then the question is, can we take this radon transform and recover the original image? If you only have one projection, clearly there's not enough information, right? Because many objects could have the same single projection. So it raises the question is, how many projections do you need? Well, we'll start off by assuming you have an infinite number of projections. So you have this projection for every angle theta. So in that case, what happens is that you have a 2D function, and for each theta, you get a 1D function. But now you get a 1D function for each theta, and there's a continuum of thetas that go from, say, 0 to pi. And beyond pi, you're getting the same information back again, right? So you only have to consider 0 to pi, because projecting this way is the same thing as projecting that way. So you only go to 0 to pi, but then that's essentially like a 2D image, and that 2D image is called a sinogram. So what ends up happening is that you have something that looks like this. So you have like, this is a projection. So this is some theta. So let's say that's a theta up. So this is 0, this is pi. So this is pi over 2. So theta equals pi over 2. You'll have some function. You could put it along here, right? So you could just take the values and populate them along along a row of a matrix, essentially. I don't like to call this a matrix. I call it a 2D array. So it's a row of this 2D array. And then you could do that for every angle, okay? And you could populate this. We'll see this in a little bit. And this is a 2D image. This 2D image is known as a sinogram. Why is it known as a sinogram? Because it's usually not displayed this way. It's actually usually displayed like this. This is theta. And this thing is r. It's usually done like this. Now, what will happen is this. So you're taking a projection. Imagine you have a bicycle. Everybody knows what a bicycle is, right? Okay. Oh my gosh. That's a bicycle wheel. Tire. Wheel. And there are, of course, spokes. Okay? And there's a hub in the center. And you could take the bicycle wheel and hold it like this and spin it, right? Everybody can physically imagine that, right? And now you put everybody knows what the stem is, right? Like you could either have a Schrader or a Presta stem, right? And now you stand over here, and you look at this. Okay, you're looking at it. Now, if you spin this tire around as you're looking at it, and you're looking at the tire, it's spinning, and you're looking at the stem, the position of the stem. It's going around in a circle like this, right? But if you look at it from far away, it's going to look like it's just going up and down like this, like a sine wave, the stem, right? Because as this thing rotates around, the stem looks like it's just going up and down in a sine wave, right? So when you look at a sinogram is like a projection, and if you plotted out the position of the stem, what it'll end up happening is it'll look like this, right? Do you believe that? That would be the position of the stem that you're seeing from the side. So when you look at sinograms of objects, they look like sine waves, and that's why they call them sinograms, okay? Because the dense objects in the image you're looking at look like, plot out little sinogram for things, and then you're trying to take this sine wave thing, and you're trying to map it back to that position. That's the intuition. All right. So this thing is called a sinogram because it tends to have sine waves that look like that. Now you usually don't get 360 degrees. You only usually get 180. So you only see a half of a cycle of the sine wave in the sinogram. All right. So you have some intuition about that. So now here's the thing. Now there's the miraculous piece of things. So this is the radon transform. The radon transform takes you from the image to the sinogram, right? Maybe I'll draw that just to emphasize. So you have an image. So this is X, and this is Y. You have like an object over here, and then over here you have the sinogram. This is image. This is sinogram. And it looks like this. By the way, the phase of the sine wave is determined by the angle of this object relative to the coordinate system. And the amplitude of the sinogram is determined by the distance from the center of rotation. Okay? So it's almost like a polar coordinate transform. And sinograms are a little bit like Fourier transforms in the sense that you can transform between the image space and the sinogram space and back. But the thing that makes it different than a Fourier transform is a Fourier transform is an orthonormal transformation. This is not, okay? So, but you can go back and forth between sinogram space and image space. So, okay, so that you have this transform. Oh, and I'll just emphasize one more time. This thing here is called the radon transform. So the trick is, how are we going to do the inverse radon transform? How are we going to get back? Well, the thing that makes it all work is this thing called the Fourier slice theorem, which is a little miracle. Okay? It's kind of a beautiful thing. It turns out that if you take the Fourier transform, the continuous time Fourier transform of the projection, and you take the 2D transform of the image, they're related by a simple polar coordinate transform. So in other words, if you take this the Fourier transform of the projections, it's just the polar coordinate transform of the 2D Fourier transform of the image. That's the amazing thing. Okay, maybe I have a diagram here. I can show you. Well, okay, okay, so it works like this. So if we have, so you have, this is theta, and this is R. This is the sinogram. You take the Fourier transform. This is, continuous time Fourier transform. So you take the Fourier transform along the rows, and that gives you something which is, yeah. Now this becomes what I'm calling rho. I use the letter rho for the Fourier transform variable, and this is theta. Okay, and then this thing, this is a polar coordinate transform, X form. Okay, this becomes, this is the f of uv, and then this thing is the continuous space Fourier transform. So, and this is the image. And then this thing here, this is the radon transform. Okay, so that's how it works. So the image, you can take the image and you can get a radon transform. From the radon transform, you could take the Fourier transform of the time along the rows, and that gives you this thing over here, which actually doesn't really have a name. That's this thing, p theta of rho. And then you can take you could put, this thing is a polar coordinate transform of that. So you could take this data and just plot it in rectangular coordinates, and then take the inverse Fourier transform and you get the image back. That's the beauty of it all. And this is actually how people do it sometimes. There's different algorithms. I'll describe them to you. Now, the question is, so basically, if you take the transform of the rows of the radon transform, what'll happen is that, and that's just the 2D Fourier transform in polar coordinates. So you could just plot it out in polar coordinates here. Now, you might ask your question, well, why is this theorem true? Well, the proof, maybe I won't go through the proof. You can go through the proof, and you should go through the proof and just verify that the steps are correct, okay? It's basically just some kind of changing of integrals. It's just a clever thing. You can verify that the steps are correct, okay? But I'm not sure it gives it a lot of intuition. Maybe. It depends on how you think about things. It'd be different for different people. Oh, this was the curve I was looking for. This is the slide I was looking for. This is a slide which just shows that you can plot out the continuous time Fourier transform of the projections in polar coordinates, and that gives you the 2D Fourier transform. But the an alternative proof is this. If you look at the projection of an image, yeah, right, yeah.
So radon transform, we are going from what to what?
In the radon transform, this is the image, right? The radon transform just takes the projection. So along each row of here, you have the projection at a particular angle. So let's say at zero, angle 0, you take the projection. I think it's just a pure vertical sum of the columns.
What was it? The one on the top? Like what is it?
What's happening here?
No, yeah, the first figure that you have.
Yeah.
Yeah, what is that one?
So this is the sinogram.
Okay.
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 So this is the sinogram. In practice, you don't do this mathematically. In practice, you get this by some physical measurement that directly results in the measurements of the sinogram. And then from there, you can take those physical measurements, you take their Fourier transforms, and that populates. I'll show you an example next time. That populates this, and then you can use this thing here, okay, to reformat in rectangular coordinates here. And the rectangular format for coordinate transform is like this. Basically, you just plot the data out along these rays, and then you take the inverse 2D Fourier transform, and you get the image back.
Okay.
Right? And that's actually a valid way of doing reconstruction that's pretty commonly used. This is a good diagram. I'm going to keep it. Maybe I'll even draw it up. We'll go over this again next time because we're running out of time now. So, okay, thanks a lot. I'll see you on Friday. Bye.